And a simple example of an A/B test, right? And this has happened multiple times, I imagine. But yes, a simple example where it's a very common thing that you have one particular, say, experience where there is a generative model behind the scenes somewhere. Either it is ranking, either it is, say, directly chatting with the user, or it is powering a full AI agentic experience, maybe helping the customer book a flight, or maybe helping someone write code, right? But there is an LLM brain in the experience, right? And there was an existing model, Model A, and now the hypothesis is that there is the newer model, which is better because it captures or understands user intent better, and therefore results in better engagement, right? That's the hypothesis. And what happens is, you run the experiment maybe 2 weeks or 3 weeks, and then you analyze the data. And the data showed that Model B actually showed a bit lower user engagement, or essentially the treatment, right? The treatment or the experiment variation with the new variant showed lower engagement. And Model A was, say, declared the winner. So you don't change anything, you continue with Model A. And fine, the data showed what it is. You went ahead and made the decision. Now, when you went ahead and did a deeper dive, you realize the reality is that what was happening was the Model B API was repeatedly timing out. And when that happens, your system was falling back to Model A. So while you thought that in your treatment, in your test experience, it's just Model B, in reality, Model B was not reachable, right? And it was falling back to Model A. So a lot of people got Model A as experience. What made it worse was that there was an added latency because it has to wait, right, a couple of seconds for the failure, and then it falls back. So what a lot of people were really getting was not Model B, but first a delay of perhaps 2.5 seconds, and then Model A again. And when you were really comparing the treatment with the control, you were essentially comparing a lagged version of A with A. So it's no surprise that Model A remained the winner. And this illustrative example shows you, right, this is one of the many ways these systems can now fail. And this is a simple example. In the next few minutes, we'll talk of many, many other examples. But the main point is that there's many ways this can work, right? And we saw one example that, okay, the latency was an issue. But I think because most of you are not running experiments at this point, I'll maybe perhaps not spend time on this discussion, but there were many things perhaps which could have been done better. Instead of just waiting for this, maybe we would have had more monitoring. Maybe we would have had stricter conditions, fallback alerts, and so on, right? Maybe this could have been done very differently. The design of this experiment was not really optimal, perhaps, right? So that's really the theme. One theme we'll talk about, that when you have AI features in the mix, design becomes a critical component, and we just cannot do things the same way we were doing them earlier. So experiment design and measurement need to change in the AI era. Now, let's go discuss this point a bit more. So how is traditional experimentation now impacted, and what needs to be done differently? I'll enumerate a few key points, and then I'll go deeper into a few of them, right? And then I'll hand over to Vishnu. So when we usually worked with experimentation, what we usually, or what we are accustomed to, or what we have perhaps spoiled with, or what generally used to happen was that we had three things working for us in general, right? Not always, but in most cases. One, we had stable treatments. Without going into detail, things were stable, meaning predictable, that, okay, we said, okay, this person gets treatment A, means they see a blue button, so they will see a blue button, right? There's not much uncertainty around that. Once you know this person is assigned to this treatment, they will see the blue button. And they come back tomorrow, they see the blue button, right? It's a very stable kind of a treatment. Also things that, if I see the blue button, probability of Vishnu seeing the blue button doesn't really change. So there are stable treatments here. Timelines were controlled, meaning that you had decided upfront that you need these many samples or these many users. And to get as many users, you need to run this experiment for perhaps 3 weeks. So controlled timelines and then very rather controlled stuff. And then we also had relatively clear metrics. Of course, metrics is always a point of discussion and argumentation, but still, you have been doing this for a while. Standard metrics. We discussed earlier that many people use business KPIs and so on. So you had clear metrics, stable treatments, and control time. These were some key features which allowed us to experiment as well. This was really good. This is what we had earlier. And now things are changing quite a bit. Now there are many new challenges coming up. Because now the output itself is very different. The way the models work is very different. The way the system is working is different. The way the user interacts with the system is very different, right? And there are these new challenges. I'll list them first. I'll go into a bit more detail in a few of them. Okay. First is non-determinism. And most of you, I imagine, know this by now, that large language models, their output, if you have a chat model, for instance, output is text. And text is not a single binary yes or a no or a 0 or 1 always, right? Text is like long passages sometimes, right? It is giving you information sometimes. So it's not really a deterministic system in a way. Different people, minor variations in their input, very different outputs. And what you get out is a distribution, right? It's a composition, a distribution of terms. So this nature of the output itself is quite different, and that leads to some challenges, especially if you are evaluating the model output quality, as some of you in the poll had suggested that, okay, that you folks are measuring output quality of the model. Now output is not deterministic. That, of course, brings new challenges. Second is the metric, of course, is a big challenge now, because in many cases, there is no stable ground truth, right? When it is running in the field, during the treatment, right, there is no ground truth in many cases, right? So metric definition is, again, a big challenge. Satwa violations and spillover. Now, if in case you folks are not aware of Satwa, what it essentially means, two major things. Okay, one is that the treatment you get, right, is consistent. It is fixed. This is what it is. This is what you will see. You will see a blue button. You will see a blue button. And the other thing is, there's no interference, meaning that someone else doing something in the control does not affect anything from me in the treatment. So these groups are different. They are not interacting, right? This is essentially it, right? There is no leakage between the groups. What someone does in the treatment doesn't affect anything in the control. This is very separated. And this is Satwa. But Satwa is violated. And there's many reasons, of course. First of all, the model itself evolves, right? So what I see today, and if I come back 10 days later, the model in the meanwhile has learned. The agentic system has learned a lot. So what I saw on day 1 is different from day 10. So therefore, the treatment itself has changed now, right? I'm not looking at one model. I'm looking at one version of the model on day 1, another version on day 10. So now the model itself has changed. The treatment has changed. And also, because of a lot of things which we'll discuss perhaps later, shared infrastructure, shared knowledge bases, and so on, or feedback loops. Feedback loops is a different topic, but this also happens through this. There is spillage, meaning that actions in the treatment can affect people in the control. So this is a major violation, and this is something to be extra careful about. This is another big new challenge. Fourth is the feedback loop. And it is also called a flywheel problem, where the model does some things, and then based on the model, you take some actions, and those actions, in a way, go back into the model as feedback. And then there is a loop. And because there is a loop, the model is now evolving in a certain direction, right? And the loop, and because of this, multiple things change. The treatment itself is changing, the model behavior is changing, the metrics are being affected, and so it's not. I mean, it's of course it is messy, as you can imagine. And there are these few problems, but there's also other challenges. And depending on if you have a lot of time, we'll go into detail. But there's novelty effect. When there is a new feature, a lot of people flock to it just to give it a try. it's a nice thing, it's a fun thing to try out. Maybe they engaged with it, didn't really influence anything. Perhaps they tried it out and then left it, right? So it has some novelty effect. In the beginning, perhaps usage is high, but then it kind of goes down. So if you have an experiment for a very short duration, you will see that, oh, engagement is super high, but impact isn't really there. There's also something called a primacy effect. The primacy effect means that when the user starts using it the first time, they're not really very comfortable with the environment, perhaps, or how to work with this agent and so on, right? But after working with it for a few days, after a couple of weeks, perhaps, they use it very differently. Yes. So their usage also adapts, right? Users also adapts. So now the user behavior itself is changing, even if, let's say, the treatment is not changing, right? So this happens when we have these innovative or vastly different experiences. Then there's some very interesting stuff like prompt sensitivity. This is a very interesting one. Unfortunately, we cannot discuss in detail, but let's say you have two different variations of the model, right? Model 1, model 2. And we know by now that if you are using GPT 5.3 versus GPT 5.1, you have to prompt slightly differently. And we also know by now that models are sensitive to the prompts. So if the system prompt is slightly different, or even, let's say, significantly different, let's say, between treatment and control, then there's a very high chance this itself is causing quite a bit of difference in the experiences and unintended, right? So again, prompt sensitivity is a hidden confounder, which people are not even considering that this could be something which is really ruining your experiment. A third thing is long horizon compounding effects. I think the easiest way to think of it is an agentic system where there's not one single decision, but you interact and with the system back and forth, perhaps, and there's a bit of error, perhaps, right? Or there's a bit of bias in the agent. The first time it takes an action slightly off, second time slightly off, but over 5 actions, it's going in a different direction compared to where you want it to be. So these effects compound. And also these systems now, the way we're designing them, they're also learning, right? Updating. Knowledge bases are being updated. Feedback is being recorded. So this compounds. So the effect is also a couple of very interesting things. One is the circular bias, where folks are using large language models as judges. What does that mean? So you use a chat model. A chat model gives you text output. And you have like thousands of conversations. I'll talk about this example in the next slide. But if you're using a large language model as a judge, you have some new problems come up, which people are not really considering, but this is something to be really wary of. And finally, variance shifts or power analysis breakdowns. This is a bit of a deeper, more challenging thing to understand. So maybe if time permits at the end, we can cover this. But this essentially means that models in their outputs can be very different in what the output comes out to be. And then because of this, when you do calculations, how many people do you need, what is statistical significance, and so on, all that is really ruined if you don't do it really well. And this is a very big challenge right now with large language models. So as discussed, I will go into detail for one of them, so which is LLM as a judge. So let's take this example where you have some e-commerce company. They have 50,000 conversations per day, and there's a new model, there's an older model. You want to see if the new model works better, but this is a chat system, right? And you want to assess response quality. Of course, humans going to 50,000 per day doesn't make any sense. So you say, okay, you might say sample, but still doesn't make much sense. So what is a fair thing to do is use a large language model as a judge. So take these 25,000 here, 25,000 there. Large language model goes through all of these responses, takes the initial context of the user query, the response, and gives a score out of 10. Like 6, 7, 8, 9, whatever, right? Gives a score to the response of the LLM, right? So it assesses the LLM responses in the treatment, in the control, and gives them scores to both the models. Sounds very logical. Sounds like the only solution perhaps in many situations. What is the issue? Number one, it is known that large language models, if you don't manage it well, they prefer verbosity. So some response which is lengthier and has more structure is understood by LLMs as having higher quality. So it might score it a bit higher just because it is longer and well structured, not because perhaps it was meeting the user's requirements. Okay, so there is this bias. Number two, there is a self-preference bias, and this is well studied. So if you give Claude responses from Gemini and Claude will prefer its own responses, its own family. It's a Claude model, right? Gemini prefers Gemini, GPT prefers GPT. This is also known. So if you are testing, if your judge is Claude, and if the two different competing models are Gemini and Claude, you kind of know who the winner is going to be. Finally, there is a circular training loop. So let's say you judge uses all of these responses, and there's you store all of this, the good responses, and you feed them back into training data. And what happens is the next generation, right, the best prompts, everything, the next generation or next iteration of the model will effectively have taken this feedback from the judge. And what is happening now is effectively the judge is deciding what happens in the next iteration. And in the next iteration, of course, when this model comes as a contender, the judge will love it because the model has learned, right? This particular assistant has learned to say, make the judge happy, right? So this is really very tricky. And if you don't pay attention, this is a very insidious way in which things can be completely off. So the key takeaway, right? All of these issues are very real, and these are well documented now, right? So one of the main things to take away from this example is that LLMs are not neutral evaluators, right? There are many biases here, and we haven't even talked about the kinds of biases, depending on training data and so on, and domain. And there's many more issues, but still, even without those, right? LLMs are not neutral evaluators, and this particular is a very tricky challenge, and you really have to be super careful in choosing the right metrics, maybe having holdout groups and stuff, and maybe controlling how you train and update the models to kind of mitigate this particular risk. Okay, so that's one example. I'll take another example, which I'll keep it simple before I hand over to Vishnu, which is metric definition, as some of you also flagged as a big issue. And let's take another simple example, right? This is an AI styling assistant on an e-commerce platform. Customer comes in, asks for some recommendations. I want to wear this kind of stuff. I want to look like this, and so on. And the system gives them outfit recommendations. Now the question is, what is the success metric for this? And depending on who you ask, you get a very different response. The product manager would say something which measures engagement is good. Session duration is a good metric. The data scientist might say, okay, add to cart rate is better because it is closer to the conversion, right? AI engineer might say, of course, I want to understand the response quality, right? I want to update the model and so on. And the business team might say, conversion is what it is. I don't care what you're doing behind the scenes, conversion. And as I said, depending on who you ask, this is very different. And the output is open-ended in this, meaning that, of course, there's no perfect answer for this, and Vishnu will talk about this in great detail. Another thing to remember now is whatever your objective is going to be. So let's say you want them to add to cart. You will practically, in most cases, you will tell the agent that your goal is to make them add to cart, right? So assistant will influence the metric it is being measured on, and in a very direct way, right? So maybe it's not really the best. But anyway, also the differences between control and treatment and stuff might be a bit harder to see in the shorter run. That's another topic which we'll again Vishnu talk about. But there are many challenges here when you're talking about metrics as well, right? So I think with that, let me know if there's any questions at this point. Otherwise, what I'll do is just summarize this and hand over to Vishnu. So overall, what we're saying is that with AI features in there, in general, we have these questions, but with AI features, questions only increase in number. The output is not like a 0, 1, a binary thing. The AI assistant behaves a certain way, so you have to be super careful while defining these metrics. And if there's no questions, I'll hand over to Vishnu, who will talk about the measurement part and defining metrics. Vishnu, over to you. If you'd like to share your screen, please do.
Thank you, Rahim. Let me share my screen. Thank you, Rahim. Let me share my screen.
Yep.
Just let me know if you guys can see the screen. Are you able to see the screen?
Yes, Vishnu, we can.
Great, thank you. So thank you, Ray, for addressing the last slide, which is mainly speaking about the how do you decide the success matrix. So let's deep dive into the same topic, how we can measure the successes in experimentation as well as the AI-powered experiences when we have different products, traditional versus the new AI features and products, how we can measure them successfully. Let's deep dive into it. So how do we actually measure the success in AI-powered experiences? This is something that always have a question for everybody, right? So looking at that one, let's go back a little bit and think about how our traditional product looks like. So it has a very easy flow, deterministic flow. You click on the button, you go and purchase, and then you will generate the revenue. That's a success. So this is basically a linear journey, which is a single conversion point, easy attribution. But currently, the AI features of the product a bit different. It's not like a deterministic flow as Rahim said. So it's more of a non-linear journey and probabilistic. Model changes, the behavior changes, everything changes. So how do you measure the success? So let's take an example of AI product. Like if you go to the ChatGPT or Cloud or any of the AI prompt, if you ask the plan my vacation, AI will respond to you. You will read it, think about it, edit it, you modify it, and try to again get some answers from the AI. So this loop will keep continuing, right? But at the end of the day, when you do the conversation, do you really click directly on the conversion? It's not really straightforward that whether did the AI succeeded in clicking and making a conversion. We can't say from the clicks alone, right? So what are the challenges then? How do we measure them? There are multiple paths. We have invisible value. There could be a weak attribution. In such scenarios, traditional metrics also measure some actions, but those are not sufficient to do the measure of the AI product. So AI success is often about outcomes, right, that happen outside the system. For an example, if you look at the AI flow here, you have the prompt, you send it to the LLM, then you get the conversation done, you had some clarifications, and based on that, you try to make a decision. But do you do the purchase? Direct conversion can happen here. Maybe not. You make a call and then maybe go to some other website or something, and then you make a call and make a purchase there. So this is mostly it happens outside the system. So then how do you gonna measure this success overall? Is something challenging. So in that sense, we'll deep dive into what are the success metrics, because I see from the poll itself, there are 50% people who are really struggling with the success metrics. And if you can't measure it, actually you can't improve the whole product usually. So let's deep dive a bit more into this. First thing we should ask, why do we need them? Why should we care about them, right? If you want to have, just take an example of, like, for an example, in any organization, they have a vision, mission statement, they have a business strategy, how we plan to win, something like that. And they have certain objectives which are very much aligned to the business strategy, which we call it as like, what do we want to achieve at the end of the day? And something called key results, right? How do you know how we are progressing towards our objectives, towards our business strategy, and which leads to our vision, right? And if you want to measure the results, it's a matrix. How do you measure the key results? Through the experiments, through the different things that we do. So this is how we should care about it. So basically, it's an OKR planning that goes into the always goes into the C-level executive business strategy. It talks always about the OKRs. OKR is nothing but like objectives and the key results. Objective is what you're gonna achieve, and key results are something like short-term measurable things, which is done through the metrics, right? So then, in general, in the strategy, what you look at it, you look at the long-term goals, either growing revenue, improving retention, increasing satisfaction, reducing the cost, driving innovation. And then you align your objectives towards it, like translating the business strategy into breaking down into a measurable objectives, which is again the long-term goals. And this should be supplied with the key results, which is a short-term measurable results, and that will lead to generate the matrix. So that's how we define the success metrics, which are helpful in our business decisions. Okay. uh, if any question, just stop me, because I'm just seeing my screen. Let me. Okay.
No questions.
Okay, perfect. So let's move on to the next slide. If we are struggling about the success matrix, right? So how do you decide about the framework? Is there any framework do we have? How should we decide about? Like Rahim said, right? AI engineer has its own KPIs. Product engineer has product analyst has its own KPIs. Product manager has its own KPIs. So who and how should we consider the KPIs to be measured for any experiments, right? So I want to give you a like kind of a mental model to you, which will talk about three different metrics and three kinds of a different matrix, which will do the three different jobs altogether. What are those then? So usually when we look at the OKR, it's objective and key results, which needs some framework to define those metrics. So let's talk about one of the pillar of the matrix, which is called the goal metric. Either you can call it as a true North Star metric, which reflects what the organization ultimately cares about, which is directly tied up to your objective and the long-term mission, and it is not easy to move in the short term. So ideally, that's like very important one. And when you're deciding these things, you should ask some questions. Why does this product exist? Which product you are working? What type of product your company is delivering? And what does the success will look like for this organization? So this question should lead it to you to defining the North Star metric. And now this is the North Star metric. Then how do you move this North Star metric? So there is a second pillar which comes as a driver metric, which speaks about like you can talk this matrix as a surrogate matrix or a driver metric, which is the indirect predictive matrix for your goal metric. So it is a faster moving than the goal metric, break down to the steps that lead to the goal, and it has its own framework. So driver metric is basically, if you look at it, it is a short-term actionable, I would say, a matrix, which is give you the actionable insights. And based on that, you lead to the goal metric, and your goal metric will move accordingly. But now deciding driver metric itself needs to have certain structure, right? How do we decide them? So there are two different frameworks which are mainly focusing on the driver metric. One is called HEART. That means you should look at the user perspective, look at their satisfaction, happiness, engagement, then adoption of your features, then retention at the end of the day, and how the success looks like at the task completion, conversion rate, and all. Then we have something called ARR, which is the acquisition, retention, and referral revenue. Okay. And then something comes as a guardrail matrix, protect this business. So ideally the goal metric, driver metric, and guardrail metrics are very important at the same time, which is like guarding against your violated assumptions, right? So goal is maximizing the registration, for an example, but guardrail metric could be per user engagement should not drop. Even if you are actually trying to improve the registration, it should not drop your engagement. So you are protecting the business as such. How they come goes together. Driver matrix will push the goal matrix, and guardrails will protect the system. For an example, just to give you what looks like the North Star matrix, for a Google example, it's search queries per year, which is what would be the driver metric for this one? Average daily queries per user, something like that. So for an example, Netflix could have the subscriber per year. And if you want to run an A/B test, which is a recommendation system, and you want to see the engagement, then probably you will look at like average daily money minutes per user. And how do you measure the guardrails? Is your cancellations, the subscription cancellation should per day should not go decreasing. So that will protect your business. Moving on to the one, you should, I think this is more of a like how you formulate your effective matrix. It's more about like, you can go through this slide afterwards. Mainly this is about like how you formulate. You can have a simple and stable goal, simple definition for the goal matrix, and it should be a stable one. And for the driver matrix, it should be aligned with the goals and it should be actionable. And at the end of the day, these two metrics are successful or not, are we driving any outcomes or not, that can be measured through the surveys, UX studies, user research, and focus group. This is how you should formulate it. But I would keep it for yourself to read the slide in the recordings afterwards. Moving on to the next one, which is very critical piece of the experimentation. Any metrics for our experimentation and overall evaluation criteria, right? How do we decide if an experiment should ship or not? Now we have some framework for the matrix, designing the matrix. Now look at the experimentation matrix, how it should be. The experiments are usually duration of 1 week, 2 weeks, 3 weeks, depending on your product and how you design it. It should be a short-term and measurable. So your metrics are short-term and measurable, then it can be helpful for your experimentation. And it should be observable during the short experiment window. It should be easily computable. And for an example, what could not look like an experiment matrix? If you do the post-purchase satisfaction, which is a valuable but really hard to measure during the runtime, right? So it cannot be an ideal matrix for the experiment. So we should avoid those things. Now look at, many a times it happens that during the experimentation, we look not only one matrix, we have the multiple matrix, and we have to evaluate them overall as an overall evaluation criteria. So how do we make a decision? Some of them are working, some of them are not working, and what you should talk about. So when you are deciding overall evaluation criteria, that means you take into an account all the metrics. So either you can normalize them on a certain scale, weight them based on the percentages, and sum all the weighted, sum them up on the weighted sum. And based on that, you can come up to a decision where we should move, you will get a signal to move ahead or not. But in practice, this is really difficult to wait and find. So in the complex real systems, it's really difficult. So how do we come to a practical decision making where you have like decision making when to ship and when not to ship? So I want to break down in 4 different scenarios when the max through the overall evaluation criteria, how you can take a decision of the shipping a product or not shipping a product. For example, you have multiple matrices, all are flat in your A/B testing experimentation. All of them are positive. I mean, like either all of them are positive or flat, and one of them is positive. That means there is nothing negativity. So you can ship the product basically. And if there are key metrics, one of the key metrics is negative, then ideally you should not go for shipping it. This is how you should make the business decision on the metric basis. Now, when there are all the metrics are flat, what the decision you should take it? This is clearly a no signal. You need to boost your power of the experiment. You need to rethink about redesigning of the experiment and come prepared with another trial with the new experiment design. So there is a no signal at all. So we should not go with that one. So we need to boost the power. Lastly, what happens is that I talked about overall evaluation criteria, right? So when we have mixed results, some of them are positive, some of them are negative, then you definitely need to go with the weights and business decisions. Based on that, you can make a judgment. Okay. Now, in summary, I want to say that to design a robust shipping any gate balance computational OEC matrix, right? So always maintain absolute clarity on the distinct roles of the goal matrix, which are the predictive driver matrix and validation feedback loops. So based on this one, ideally you need to look at different feedback loops, business decisions, judgments. There are multiple things comes into the picture, and based on that you can actually evaluate the experiment results and make a decision. Now, I would like to just touch base with respect to the example that Rahim has said earlier. Because he said that we have some AI shopping assistant for an e-commerce platform, but we were struggling about defining them, right? So, for if we are struggling about defining them, then how does the AI improve the customer purchase journey if it is our code? Yes, please go ahead. Okay, I'll continue if there is no question. So I'm just revisiting the slide of Rahim said earlier, right? So let's say we have to have a North Star metric and order completion rate. And then what are the driver metrics for this one? Product discovery rate, then task completion rate. These are the things that can be done. And then there should be some guardrail matrix because it's an AI shopping assistant. We can measure the hallucination rate, response latency, trust, and these are things. And finally, we can look at the conversion abandonment, average turns, all of these. So ideally, this is if you give the framework of this, like North Star, driver, guardrail, and diagnostic, you will be able to design for of the AI products some of the KPIs clearly. Now, another example, which is a real world case study that I would like to highlight. For an example, there was an A/B test eBay has done. There were 300 developers that has taken into the experiment. They wanted to use the GitHub Copilot versus the control group has no GitHub pilot. They will be given the regular assignments and they will be working on without the GitHub Copilot. And they're trying to measure whether the GitHub Copilot will help us to improve anything, or it's just a kind of not worth to invest on the GitHub Copilot in general. So they wanted to see the main North Star metric was to sustain developer productivity. They should be faster, high quality, and deliver across the software development lifecycle. Not just like faster typing, but they should be actually productive and more efficient. And this is very difficult matrix actually to define for the developers. Then they decided with some of the driver metrics to go about it. Like if you look at the results that they came up, the code acceptance rate was almost 27% up. The pull request creation and merging time reduced by 17%. Lead time for change was also reduced by 12%. So this shows that there is a lot of productivity shown versus the people who are in the control group. So ideally looking at the driver matrix, it has clearly shown that there is a sustained developer productivity, which is a faster than the previous one. And to measure this one, they also did the guardrail matrix as an pillar to make sure that whether the productivity has increased, but are we compromising on code quality. So they used the Sonar. They found that Sonar is a code quality check tool, and they watched that both the groups. But the result was like they were flat. Watch closely. Both of the group has same quality of the code, and code accuracy was almost 60% up. And the generated docs through the accuracy was 70% up, which shows that it has a really meaningful impact over the developer's productivity, and they rolled it out. So this is how actually you should measure the real world AI use cases with respect to your day-to-day things that you are building, right? So with having said that, I think if there are any questions, I'm happy to answer that. But the mental model should be like, you should have certain metrics, which is the log thought, then driving metrics, and then guardrail, protecting your system. So if you follow this particular mental model, probably you will have you will come up with the right thought process to build the matrix, and that will be your success matrix. Yeah, that's pretty much from my side. If any questions, just let me know. I'm happy to answer those questions.
Yeah, I think there's a quick question in chat which is about code acceptance rate. I think she's asking whether code acceptance rate 27%, is it increased or is it decreased? That's what the question is.
Code acceptance rate was increased. That means it was accepted by the GitHub repository, which is like kind of increasing your, it is not getting rejected for any of the reasons. So it's a more of a productivity increase through the code that is submitted through the AI. The time has improved. That means the time spent by the developer on control group was like kind of more double than the time spent by the people who are working with the Copilot. So the productivity has increased with the time, that I would say.
All right. Well, thanks, Vishnu. I think, and one of the most interesting things which caught my eye was that there was no single metric, right, as a North Star.
Yes, exactly.
This is also super interesting to see. Anyway, so with that, right, I think we get the overall picture. Let me just summarize this, right, and also kind of share one perspective on the future of experimentation as it has evolved, right. The main thing, the key issue here is that classical A/B tests were designed for static interventions. Right? There were assumptions about users being independent. The measurements were over short horizons. Metrics were also clearer, as we discussed earlier. But now we have AI systems which are, of course, dynamic, very commonly interconnected, and usually they are also continuously evolving. So we are dealing with a completely different beast here, and we need to therefore rethink what experimentation means in this case, and design of these experimentations becomes a really critical skill now, design and guardrails. And I'll just very briefly touch upon this, right? Again, details perhaps in the future session sometime, but yeah, what we really need, one really key feature or one key thing we all need to work on, the key aspect is faster testing, adaptive faster testing. So sequential testing is one method where what we do is we continuously keep monitoring. So historically, we say we don't peak, we don't stop. There's many challenges over there. But now we say, okay, keep monitoring. Whenever you look at, when you peak, you apply some sort of a statistical correction, but keep monitoring things. Extend experiments automatically when signal is inconclusive and so on. So you want faster testing. You want to have a lot of guardrails. So because if you're having these quick decisioning happening, right, or snap decisioning, or quick actions happening, or let's say variations changing and so on, you also have to have like really robust guardrails around the system for these things to happen. And then the other thing which I like to highlight is that earlier even Vishnu was mentioning this, right? That ship, no ship, but it was also about wait, get more evidence and so on, right? So but decisions were largely binary earlier, but now we are going towards continuous learning in a way. And I'll talk of this perhaps later, but yeah, continuous learning as well, where it's like, okay, this has worked in this segment, it has not worked in this segment. You need to quickly go towards the next iteration, taking this into consideration and so on, right? So there's also a continuous learning aspect without necessarily a very clear binary decision. For more reliable assessments, as we've been discussing, generally the importance of a holdout group is only increasing. A holdout group essentially means that there is a group of people, 5%, 10% of your overall traffic, who do not see any experiments whatsoever, right? Only the final rolled out features. That's all this. You do not see any of the experiments which are going on. And this really helps you evaluate true impact of this intervention. This helps you in many ways. This is a long-running continuous, right? It helps you in many ways. It helps you handle novelty effects. It helps you tackle primacy effects. It also helps you see, slow changing user habits. What was the true impact? It helps you see the impact of the model evolution. And so having a control, it's a continuous control group, which is called a global holdout group, is really valuable. Many companies have this incorporated, but if not, then this is high time we start incorporating in your own company as well. The other thing is implicit signals versus explicit outcomes. As Vishnu also mentioned, not all the outcomes, eventual business goals, outcomes are not part of the experience, not in the chat. So you have to look at implicit signals. Metric taxonomies become super important. Another very important topic is looking at tail behaviors. So the averages are generally deceiving, but with AI systems, it can be even more so. Because there's also this notion of catastrophic failures where system completely just breaks down, which is these systems are a bit more brittle than people think it is, right? So you take a look at the 5th percentile, lower percentiles, take a look at the number of catastrophic failures and so on. Keep a very keen eye on them because they are very misleading. Okay, and generally, I mean, the new way is that you're now not testing one single change, but you're monitoring a system. Instead of having a 2 to 3 week experiment, you're having a continuous causal infrastructure, and maybe multiple bandits running and so on. Instead of ship, don't ship, you have a learn, adapt, constrain kind of a system. Perhaps earlier you knew users are independent, but now you understand users are interconnected. You saw the example of eBay where they didn't even have a single North Star metric, right? It was very qualitative kind of an assessment on a smaller sample size of just 300 people. So there is the increased importance of decision making under uncertainty. And again, for doing this decision making under uncertainty, you need very good understanding of the business. You need good risk understanding of the risk, the payoffs, also good statistical thinking and so on, right? So I would say this whole, the way it is evolving, statistical thinking and decision making and judgment is becoming even more important because AI is now helping with the easier parts, which is calculation. So that's overall just stay epistemically humble. This is the wisdom Yoda is also giving us. Okay, so thank you, folks. Then that's what we had. If you would like to stay connected, of course, you can find me on LinkedIn. Vishnu, you didn't share your LinkedIn, but you can find Vishnu also on LinkedIn, and you can join on LinkedIn. Happy to discuss things, AI, experimentation.